Good morning. So, in the last class we had seen that the priority inheritance protocol can avoid priority inversion, and we had shown that this priority inheritance bit was not set in case of the Mars Pathfinder, and consequently there were sort of infinite delays and the system resets were occurring and we were losing data, and that was avoided by setting the priority inheritance bit in the Mars from the Earth station itself, and that was avoided. But nevertheless, as we had shown in the last class, this scenario that there are two tasks T1 and T2, even if and T2 is having a higher priority than T1, and there are two critical sections which are being accessed by both the processes in a particular sequence. So, first say T1 started and T1 entered the critical section S2, and while it was in the critical section S2, T2, the higher priority task, started and entered the critical section S1. No problem up to this, because they are two different critical sections. But at this point that is at time T4, the task T2, which was having higher priority, wanted to enter the critical section S2, which was already acquired by the lower priority task T1. So, consequently, the priority inversion took place and T1 got the priority of T2, right. And so, T1 continued with the activities in S2, and while in S2 that asked for an access to S1, which was captured by T2. Now, you see, either way I invert the I change the priority now, there will always be a deadlock situation. So, although priority inversion, sorry, I am continuously making the mistake, although priority inheritance protocol avoids the priority inversion scenario, but still it is not free from vices, that is, deadlock can occur. And in order to avoid that, another variety, a slight modification of the protocol was proposed, and that is called priority ceiling protocol. We will rework the earlier example with this priority ceiling protocol, but before that let us try to understand what this priority ceiling protocol is. The priority ceiling protocol solves the priority inversion problem. So, priority inversion is also solved and deadlock is also avoided. What is done in this case? For each semaphore, like in the earlier example we had two semaphores S1 and S2, a priority ceiling is defined. And what is that ceiling? That ceiling is the value, the ceiling value is the highest priority of all the tasks that may lock it. What does it mean? What does this mean? The highest priority of all the tasks that may lock it. You see, there are a number of tasks, all right. A number of tasks are running concurrently, and each of these tasks can ask for different resources, and each shared resource is protected by some semaphore. Therefore, at any point of time when, say, there are tasks T1, T2, T3, all right, out of which T1 and T2 are sharing semaphore, are sharing a particular resource, and that resource is being guarded by semaphore, say S or S1. Now, out of this T1 and T2, suppose T1 has the higher priority. Therefore, semaphore S1's ceiling value will be that of the priority of T1. Let me explain once again. So, you see that there are number of tasks T1, T2, T3, T4. All are executing, and this one requests say resource R1, which is guarded by semaphore S1. All right. This one asks for resource R2, which is guarded by semaphore S2. This one asks for resource R1 at some point of time during its execution, and therefore, its semaphore is guarded by S1. And this resource is guarded by S1 because that is a shared resource, and I do not know a priori who will request for the resource when. Okay. So, T4 is also asking for resource R2, which is guarded by semaphore S2. So, I have got two semaphores S1 and S2. So, what will be the priority of S1? Now, suppose out of all these tasks, T1 has higher priority than T2, and T2 has got higher priority than T3, and T3 has higher priority than T4. Say. Now, semaphore S1 is being held or not actually held right now, can be held by task T1 and task T2, task T3. So, out of task T1 and T3, T1 has got the higher priority. So, the ceiling of priority ceiling of S1 will be that of the priority of T1. Similarly, between T2 and T4, they are contesting over a semaphore S2. Therefore, T2 having higher priority than T4, the ceiling of S2 will be the priority of T2. All right. Now, let us see what happens. So, once again let us read this with this explanation. For each semaphore like S1 and S2, a priority ceiling is defined whose value is the highest priority of all the tasks that may lock it, that is the highest priority of the task that uses that resource. Clear? Now, when a task Ti attempts to execute one of its critical sections, that is say PSI, wait on SI will take place, P of SI will take place, it will be suspended unless the priority of SI, that particular semaphore, is higher than the priority ceiling of the semaphores currently locked by tasks other than T1, other than Ti. Complicated, right? So, when a task, say let me work out this example and we will come back to this, right. In the meanwhile, you may like to note down this point and try to match it with my explanation. When a task Ti attempts to execute one of its critical sections, that is tries to execute a P of Si, it will be suspended unless the priority of this particular Si is higher than the priority ceiling of all the semaphores that are currently locked by tasks other than Ti. Okay. Let us see what happens. So, I had tasks T1 and T2, and T2 was having higher priority than T1. All right. Now, as you can see here, what will happen to the ceiling of S1 and S2? who is using S1? Who is using S1? T1 as well as T2, both of them. And who is using S2? T1 and T2 both. Therefore, according to our definition of priority ceiling, the priority ceiling of S1 and S2 will be both the same and that of equal to that of T2. We will now do the same earlier task that was shown to you earlier here. The same task I will be now scheduling and we will see if deadlock occurs or not. Now, as I am showing here, T2 is having higher priority than T1, but since both of them are using S1 and S2, the priority of S2 and priority of S1 are the same, and that is equal to the priority of T2, right. I am sorry, again priority ceiling of S2 and priority ceiling of S1. So, let me just cut it out a little bit. Let me just say that ceiling of S2 is the ceiling equal to the ceiling of S1, and that both of them are the same as the priority of T2, right. Now, once again I bring into the picture the earlier example. Okay. So, first T1 is starting and T1 is starting from time T0 to T1. So, here also we will do the same thing. T1 is starting, let us mark the timeline first. So, this is T1, this is T2, this is T3, this is T4. So, initially T1 starts and at T1 time T1 it asks for S2, it asks for resource S2. So, which is guarded by semaphore S2. So, now it is within the critical section, right, it is within the critical section. Now, so this is within S2. At this point T2, time T2, T1 arrives. So, T1 arrives here and T1 having the higher priority will carry on up to T3, right. I am sorry, this is T2, it will carry on up to time T3. At this point, as in the earlier case, it is asking for resource S1. Okay. So, at this point it is trying to perform PS1. Now, under normal circumstances, as was in this case, that is in the case of priority inheritance, PS1, it could continue, right, it could continue, and here there was a change, the priority inversion took place here. But now, according to priority ceiling protocol, before I allocate the resource corresponding to S1 to T2 to this task T2, I will have to check. What do I check? I will check the ceiling of the priority ceiling. So, I find that it can get the resource. Our rule is that it can get the resource provided there is its priority is higher than the ceiling of all other tasks, but that is not the case. Here S2 has been already entered and it is being used, and the ceiling of S2 and the ceiling of S1 are the same, it is not greater, right, this one is not greater. Therefore, it cannot actually perform this PS1, this one is stuck, this cannot be performed. Instead, I will allow this one to go on, and maybe somewhere down the line it asks for PS1, and it will get PS1 here, right, because that one is waiting. It will complete PS1 here and then perform VS1 here, and as it does VS1 here, then T2 man can again start executing this S2, right. Thereby, we are avoiding the deadlock scenario. Yeah, it will. This one will also do VS2. This one will also do VS2 because it has completed both, right. So, the problem that was occurring earlier is that because of this reason it was going in, right, and at this point there was a priority inversion occurring, and it was rather priority inheritance occurring. It was inheriting the priority, and was continuing, and here it was asking for the resource which is already captured, hence deadlock was occurring, right. You can see the circular waiting here, but in this case what we are doing, since we are putting in some priorities with the resources themselves. Now, this process T2 is not being able to capture, I mean here, just because it has got higher priority, it cannot really continue because of the resource conflict, and the resource that is already some resource that is captured, the ceiling of that is not lower than you. So, we will continue in that. All right.
The last one is S1. The task 2 S1.
This will be S1. This is S1. It is working on S1. Right. So, that clarifies how the priority ceiling algorithm avoids deadlock as well as deals with priority inversion. Okay. Now, with that we conclude our discussions on real time scheduling. There are many more aspects and many more issues which we can take up later, or you can study by yourself, that will not form a part of this course any further. So, next we move to another topic that is very important, that is modeling and specification of embedded systems. First, we will be discussing about models. Okay. Now, this was the original diagram that we had taken from Professor Peter Marvidal, and the different tasks were being shown. We have just, let us recapitulate, we have discussed in detail along with quite a few tutorials the embedded system hardware aspect. Now, we have talked about the system software, real time operating systems we have talked about. Now, we are coming to the specification. We are coming to the specification a little late, but that really does not matter. So, we are now, when we talk about specifying an embedded system, one simple way is natural language. Okay. In normal English, we specify what we need, but what is the problem with that? The problem is that often our conversational natural sentences are full of ambiguities, and because of those ambiguities, if there be an automated design environment, it will not be able to understand the correct semantics of the correct design intention. Therefore, we need some formal approaches. Now, the formal models, several models have been created for embedded system design. Some of the properties which are desirable for this modeling, first is the hierarchy. Okay. It is said that also from the cognition point of view, if I go on telling you more than 5 5 digit numbers or plus minus 2. So, 5 to 7 numbers, each of 5 digit maybe. After a while, after 5 such numbers, you will not be able to recall them. So, it is said that the systems becomes, if we have more than 5 objects in one particular model, then the model becomes really incomprehensible, and actually most actual systems will require many more objects. All right. If I have a complex circuit, then that will have a number of transistors, number of gates, resistors and everything, and so it is very difficult to understand, but instead if we can take them module wise, that is why the modularity is there, but there is one thing in hierarchy besides modularity. That means, we can present the system at different levels of abstraction. Okay. To start with, let me before we talk about this, let me tell you what is a model. A model is nothing but a representation, often miniaturized representation of the actual thing through some other language. Say for example, you want to describe a car, all right. Now, you can describe a car with something like this, that there is a car which has got, all right, there is a car, looks like a car. Now, let me beautify it. Okay. Now, what does it say? And I can say that these are wheels, this is the body. So, this is at one level how a car looks, all right. I can also tell a car to be, okay, here I can also say moving like this. So, the car moves and car has wheels, right. I can further break down this structure and can show the inside of the car. So, the inside of the car I can't draw, but I can further decompose this as the inside of the car and show the seats, the steering and all those things. So, these are the top level, then I can go on decomposing this. I can also say, but whatever my model is, I can say that ultimately the model must describe. So, this was a structural look wise. Here I can also try to give a functional model. A functional model would say that a car, a number of things, a car moves when accelerated, right. Is that okay? Natural language I have done. Now, moves, but provided the start is on, etc., and ignition on, etc., 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 etc. Now, while I go on describing this, I may miss out on some points. If I had written here the car moves forward with this, that would be wrong, because the gear thing also comes into picture, whether it is rear or something. So, there are number of issues that we will have to say. Ultimately, say for example, say okay, now let us look at another thing, say the model of a car versus model of a truck. How will that differ? It will be by the size, by the capacity. Now, there are many issues. So, ultimately a model will lead to a set of rules which describe the behavior. I am talking of behavioral model, which will describe the behavior of the system, and the system will follow such rules. When accelerated the car moves is a rule that holds for all cars, but that may not hold for maybe some other object. Okay. So, in that way a model should be comprehensive a model should also show the functionalities very clearly in an unambiguous manner. What we try is, we have got some model of the system, but for our purpose we will have to translate the model into some executable form. Why do we need such executable form? Because say here I have written certain things about this car. Is it complete? Does it correctly describe the thing? I could have translated that in the form of a program which could be executed, and I could have seen the result of that and see if my description is correct and complete. Therefore, often we desire the model that we choose for describing an embedded system to be executable. That means, we should be able to execute it and see its performance. With that, let us come back to this. So, what I said is, just as I had said that the car could be seen at the top, at the outside, or I can see the inside of the car, and then I can further detail, I can go to the color of the seat covers and all those things. Okay. So, those are even lower granularity of details, all right, and more detail which can come at different levels of abstraction, and that becomes easier for me to describe. There can be behavioral hierarchy. Now, coming from the car to our embedded system scenario, the behavioral hierarchy can be states. I can say that there are a number of states. A system can be something like this. There are 2 states. From this state it goes to this state, and from this state it comes back to this state. That is the thing. That is my description. At another level, I can go to the processes and procedures that are there actually running when the system is in this state. What are the things that are happening, right? So, that is a level of abstraction, and I go on decomposing them at different levels of hierarchy. There can be similarly the structural hierarchy, where I can have processors, racks, printed circuit boards. So, here for example, I can say there is a structural hierarchy at the top. Now, inside I can go in, there is a switch box, then there are racks and all those things I can describe. Another desire, so hierarchy is one of the desirable properties. Another desirable property for any embedded system specification model is to make the concurrency explicit. So, here you see this white line in between shows the concurrency, that this part of the behavior can run concurrently with this right side of the behavior. Both these behaviors can run concurrently. Okay. Now, again you can see the hierarchy. At the top level, I say that this one, if I had named this A1 and this to be A2, then A1 runs concurrently with A2. So, in a hierarchical model, I should have first drawn it like this, that there is some behavior which I am trying to describe, and it consists of 2 distinct behaviors, A1 and A2. It just says that A1 and A2 are concurrent. That is the level 0 of my description. Next, I can come to A1. I can say that this is A1 now. I could have said that this one is actually behavior A, which consists of 2 concurrent behaviors A1 and A2, and here I can say that the behavior A1 is actually, as I was showing in the diagram, there is some process followed by another process, which are sequential maybe, right. So, you see this is the top level of hierarchy, L0 describing A, and some concurrency is being shown. Here it is L1 showing A1. I can similarly show A2 to be something like this, where further I can say A2 is again concurrent behavior of maybe let me A2 1 and A2 2. This is level 1 of A2. This is a little different from what I was showing in the PowerPoint. So, why I brought this in is that I can further show concurrencies down the line. Okay. So, coming back to the PowerPoint here that I was showing here is that therefore, here no concurrency is being shown A1 and A2, and at the next level I am showing that A1 is actually a sequence of these two yellow blocks and this one is a sequence of these two red blocks. Okay. Now, when we try to do a model based design, actually we are talking of some component based design. We are, as I said, that we break it down into lower levels of granularity and the system is actually made of different components. I can say at the top that this is the first dotted line is one component and this dotted line is another component, and these two components communicate among each other. So, the other important point is the communication between the components. Now, this component, as you can see, is a hierarchical description, because this component can be further broken down into these two green components which have got their communication among themselves, and this component again can be broken down these two green components where there is a sequential communication between them, right. So, the entire behavior is consisting of components. So, that is one important thing. We should be able to show the concurrency that this one and this one, when this one is active, this one might be active, all right. Concurrency we have to show, and communication is another important point that we have to capture in any model. So, in a model we have to capture first of all the components, their behaviors and how they communicate. Okay. And wherever possible, it is very much desirable, although all modeling languages do not provide us that, timing specification should be possible to be expressed. Okay. What are the types of times that we are interested in? We have already encountered, when we discussed about real time systems, different forms of time that we are discussing. One is the elapsed time. We start from any particular point and see that from this time, this point onwards, how much time has elapsed while a program is executing. All right. We should be able to specify that, we should be able to know that. We should also be able to specify delays, that the first run of this program and the second run of this program should be delayed by a certain amount. Okay. After this completes the first run, the second run should be delayed by this extent. So, delay is another type of time that we often will require. Here is another one that is very important. I was just now, when I was drawing such diagrams like this, I did not mention what these means, as we will see later that these can be different tasks and these are also different processes. Okay. If I consider these to be processes, then suppose a task is here in this state, and this state, as I said, will consist of a number of processes and it can be executing within this process itself, traversing different substates of this. Okay. Here I specify a timeout. That timeout here is shown to be 20 milliseconds. Now, all of you are aware of process finite state machines and all those. So, if I have a state S0, from there I can exit and go to another state S1, based on some event. When some event takes place, I go out from one state and enter another state, or maybe sometimes I can remain in this state also, that is a different thing. So, here what is happening here is on an event A, it can go out, but if the event A does not take place within 20 millisecond, then there will be a timeout generated and it will go to some other state. So, timeout is another type of time specification. Not too many modeling languages provide that, but we will see later that state chart allows such specifications. And this one is very common to us, specifying the deadline with respect to the tasks, because we have seen that several times in our real time system scenario, that it must complete its execution within this time. So, when I was mentioning the desirata or what are desirable for a modeling language or modeling system for embedded system, I must be able to break them up in different components in a hierarchical manner. I must be able to specify the concurrency. I must be able to specify the computations with the within the components. We will come to that. We must be able to specify the communication, and it will be nice if I can specify the timing. Okay. So, here for reactive systems, you all remember what a reactive system is. A reactive system reacts to certain events. So, I can describe, this diagram will come time and again. There are number of states, and based on different events G, H, I, J, on these events there is state transition taking place. On F, it is coming back to this state. This is just an example. And so, there can be state behaviors. Each of these states can have its own behavior, all right. It is behaving in a particular way, doing a particular type of computation. And when the state transition takes place on an event, I may change the behavior, I may try to start doing some other task. And also there can be exceptions. Say for example, here it is shown that for all these cases, on the exception k, we are coming to another state z, all right. So, exceptions, some specific error conditions or special conditions should also be, we should be able to specify that. Okay. So, I will conclude with this. The requirements for specification and modeling techniques are, there should be, now this one I have not discussed in detail, presence of programming elements. By that I should be able to express the behavior. I have said that there should be some state, and a state has a behavior, but I must be able to specify what is done there. Although we are not restricting ourselves to the typical imperative programming like C, C++, etc., because it has got several problems. If I solely depend on that, if I only depend on such procedural languages, then there will be a number of, each of these tasks will be different threads, and all the associated problems of synchronization, deadlock, all those things, race conditions will come in, and we need supports for that. So, whether we are facing such problems or not is easier to be visualized if I go for some other modeling, and when I come to a real lower granularity of behavior or tasks description, what is to be done, there I can take help of programming languages. We will see one such method later. Now, I have already said executability, that I have done some specifications. Is it okay? How do I know? I should be able to execute it. Support for the design of large systems like object orientation or different levels of abstraction. Object orientation also does provides you the abstraction. Specific domain support, the specification must be readable, goes without saying. Portability, termination must be specified. Now, it should be easily implementable and there should be an adequate model of computation. Adequate model of computation. I stop here today with this question, what it means to compute in this environment, in this context. When we want to have an adequate model of computation, what does it mean? Because that must be captured in my specification language. So, we will take it up in the next lecture.